and welcome to lecture 5 of module 3. What I am going to do now is, so far we have been talking of Gauss elimination method in terms of examples. What I am going to do now really is to take a look at an n equation in n unknown problem and then try to see what is the amount of effort that is required in terms of the number of steps that the number of flops or number of floating point operations that will be required in order to to solve the problem using the Gauss elimination method. Okay. So again the problem that we have is going to be Ax equal to b, and then the first step that we will do is we create a matrix by catenating the columns of the vector b with the matrix A. Okay. We will consider an n by n size matrix A. So this is an n dimensional problem. Okay. And we will, although we have discussed about partial pivoting earlier, we are not going to consider partial pivoting at all in this particular discussion, simply because partial pivoting, the way computer is going to do partial pivoting is it is not going to do any kind of a computation, but it is only going to reassign the locations of the particular rows in its storage spaces. So it is very efficient when we want to do exchange of rows using for doing the partial pivoting. It does not take any computational any significant computational effort to do that. However, it takes fair amount of effort to do mathematical operations of addition, subtraction, multiplication and division. The older computers would do addition, subtraction much faster than they could do multiplication and divisions. As a result, historically people have been calculating the number of multiplication division steps and number of addition subtraction steps required independently. However, the new computers they are as efficient in doing multiplication division steps as they are in doing the addition subtraction step. So for newer computers the amount of effort required for addition subtraction is approximately similar to that required in multiplication division, one single instance of multiplication and division. So let us look at the A B matrix, and the A B matrix is going to be A11, A12, A13 and so on up to A1n, B1, A21, A22, A23, A2n, B2, A31, A32, A33, A3n, B3 and so on up to AN1, AN2, AN3 and so on up to ANN, Bn. Okay. In step 1, okay, A11 is the pivot element and R1 is the pivot row. We will use R1 to make coefficients in the pivot column equal to 0. Okay. So if we will do row operations in order to make A21, A31 and AN1 equal to 0, right, and how we do that is R2 we will replace it with R2 plus alpha 21 R1, R3 with alpha R3 plus alpha 31 R1 and so on, or in general Rj will be replaced with Rj plus alpha j1 R1, okay, where alpha 21 is nothing but A21 divided by A11. Okay. So now let us look at doing the first operation. Okay. So when we are doing the first operation, the row 1 remains the same, there is no change in row 1. So I will write it as A11, A12, A13 and so on up to A1n B1. Okay. The first computation is in computing A21. Okay. So, I will write the addition subtraction steps over here, multiplication division steps over here. Okay. There is one multiplication division step, that multiplication division step is to compute this particular coefficient alpha 21. Okay. So, now once we have computed alpha 21, we will subtract R2 minus alpha 21 into R1. Okay. As we had said earlier, we will not going to do this one extra calculation because we know a priori that this number is going to be equal to 0. So, this calculation we are not going to do. Okay. Here what this particular element is going to be, it is going to be A22 minus or sorry A22 plus alpha 21 multiplied by A12. Okay. So, this is one multiplication step and this is one addition step. Okay. So, there is one multiplication and one addition step in getting from A22 to A22 superscript 1. So, we will get this as A22 superscript 1 when we have one addition and one multiplication step. Okay. Likewise, A231 is going to be nothing but A23 plus alpha 21 A13. So, this is one multiplication step and one addition step. So, A231 is also obtained from one addition plus one multiplication step. Okay. And we repeat this for the remaining n minus 1 elements of the matrix A and one element of the vector B. Keep in mind that this distance, this number is n plus 1. Okay. There are n columns because of matrix A and n plus 1th column because of the vector B. This computation we are not doing explicitly, we are only doing all these computations. Okay. So, in this particular row operation, we have the number of addition subtraction steps are going to be equal to n, the number of multiplication division steps are going to be equal to n. Okay. So, for row operation to get row number 2, the total number of multiplication division steps are going to be n plus 1, the plus 1 is for computation of that coefficient. Okay. So, this is the row operation in order to get row number 2. Now, let us see what happens in computing row number 3. In row number 3 again we get 0 over here, okay, and we will compute A321 and again A321 is going to be equal to A32 plus alpha 21 multiplied by A12. Okay. So, this is what sorry A31 multiplied by alpha 12. So, we need one computation again in computing alpha 31, okay, which is nothing but A31 divided by A11. Okay. So, that is one multiplication and division steps, and then to get A321 we will have one multiplication step and one addition step. Here we will have one multiplication, one addition step, so on and so forth, exactly in the same manner as we had it for row number 2. Okay. So, the number of steps required over here are going to be n addition subtraction steps and n addition multiplication division step plus one more multiplication and division step to get alpha 31. Okay. And as you see, what pattern we are following is that for each and every row the number of steps that are required are exactly the same. Okay. As a result of this, what we will get is a n2 1 so on up to a n3 1 a nn 1 bn 1 b2 1 b sorry a 2n 1 a 331 and so on up to A3n1 and B31. Okay. All these are obtained through n addition subtraction step and n plus 1 multiplication division steps. Okay. And let us see how many rows are there to do this row operation. There is 1, 2, 3, 4 and so on up to n minus 1 rows. The total number of rows are n. The first row is being unchanged, only the n minus 1 rows are being changed. So what we are going to have is n plus n plus n, n minus 1 times, and n plus 1, n plus 1, n plus 1, n minus 1 times. So the total number of addition subtraction steps is going to be n multiplied by n minus 1, okay, and the total number of multiplication division steps are going to be n plus 1 multiplied by n minus 1. Okay. This is at the end of step 1. Okay. Now we will go ahead and see what happens in step 2. Okay. In step 2, A22 is the pivot element. Okay. Okay. Keep in mind that when we write algorithm for Gauss elimination method, okay, we do not create separate matrices, separate A matrices at each step. That would be extremely inefficient to do. What we are going to do is, as I have written over here, as soon as this particular computation is done, the original number that we had over here A22 is going to be replaced by A221. So although I am showing the superscript 1 over here and so on, in the computer memory there is only one A B matrix that resides in the computer's memory, and that A B matrix keeps changing when every time you do any row operation. Okay. As a result, as soon as this particular operation is done, the old value has already been replaced by A22 superscript 1. The superscripts I am using just so that I am able to distinguish the original values from the newly computed values. For no other reasons I am using these superscript. Keep in mind that you will use the same A matrix in order to do all the row operations and all the column operations. The results will be stored in the same A matrix. Okay. So now let us say what happens at the end in step 2, sorry, not at the end but in step 2. Okay, we will have this matrix again, and then we have addition subtraction steps, multiplication division steps. Okay. Row 1 unchanged, row 2 unchanged, so I will just copy those rows as they are, A11, A12, A13 and so on, A1n, B1, 0, A221, A231 and so on up to A2n1, B21. Okay. The next step we are going to do is R3 is going to be replaced by R3 plus alpha 32 multiplied by R2. Okay. Now this step first requires computation of alpha 32. Alpha 32 is nothing but A32 divided by A22, negative of that. We will again put superscript 1, again this putting the superscript 1 is really optional, because from a computational point of view it is the same variable that is storing that particular number. So we have one multiplication division step come in over here, sorry, one multiplication division step come in row 3. Okay. Now because of this particular value being 0, okay, no matter what row operation we are going to do, this value or the A31 value is not going to change. So this A31 value, the 0 that we had over here, will remain 0, it is not going to change. We are not going to waste one operation in computing this particular value. Okay. same thing as we had done before, this A32 value after the first row operation, after this row operation, because of the choice of alpha 32 is going to definitely become equal to 0. So those values are not going to change. So the unchanged value, again I am going to, over here I am going to just put them with the red color chalk. Okay. So these two values are not computed, we just keep this value unchanged and we just replace the original value over here with a value 0. Okay. This A33 is going to be equal to A331 plus alpha 32 multiplied by A231. Okay. So this again in the same manner as we have been doing before, this is how the computation goes, and this will have one multiplication step, one addition step. Okay. And as a result of one multiplication and one addition step, we will get this value as A332. So A332 has resulted from one multiplication plus one addition step. Okay. And so on, we will go on up to A3n2 and B32. Okay. Again for computing A3n2, we will have one multiplication plus one addition step and one multiplication plus one addition step over here as well. Okay. Now there are total number of columns are n plus 1, and two of the columns we have not done any addition, subtraction, multiplication, division steps at all. None of the algebraic manipulations are done over here. We have kept this number as it is and we have replaced this original number with 0, which does not require any significant computational effort. As a result of this, the total amount of effort is going to be for n minus 2 multiplications and n minus 2 additions. There are n plus 1 columns, n plus 1 minus 2 is actually going to be n minus 1, sorry, not n minus 2. Okay. So we will have n minus 1 addition subtractions, n minus 1 multiplication divisions, and plus one more multiplication division to get alpha 32. So we will have the total number of operations is going to be equal to n. Okay. Then we will do this for row number 4. For row number 4, again we will have exactly as we had in this particular case, in this particular operation, step 2 operations. In the same way, we will in the step 3 as well, these two numbers are going to be 0 and there will be one multiplication, one addition steps in the remaining n minus 1 computations. So as a result, again we will have n minus 1 number of addition, subtraction steps and n multiplication, division steps in this particular row, and this will go on up to here. Okay. So the number of times we have this is the total number of rows are n, okay, and the rows that are changing are row number 3 to row number n. So that means n minus 2 rows these operations we are conducting. So the total number of operations that we get is n minus 2 multiplied by n minus 1, and in this particular case the total number of operations are going to be n multiplied by n minus 2. Okay. So in this case the total number of operations were n multiplied by n minus 1 and n plus 1 multiplied by n minus 1. In this particular example we have n minus 2 multiplied by n minus 1 and n multiplied by n minus 2 operations. Okay. And we will continue this so on and so forth for n minus 1 steps total, and we will, so in the next step we will have n minus 3 multiplied by n minus 2 operations of addition, subtraction, and n minus 1 multiplied by n minus 2 of multiplication, divisions. So on and so forth. So total number of addition, subtraction steps are going to be equal to, okay, we go back over here, n multiplied by n minus 1, then n minus 2 multiplied by n minus 1, n minus 3 multiplied by n minus 2, and so on and so forth. So n minus 1, n minus 1, n minus 2, n minus 2, n minus 3 and so on. This is in step 1, step 2 and so on up to step n minus 1, and in step n minus 1 we will have 2 multiplied by 1 number of steps. Total number of multiplication and division steps So, total number of multiplication and division steps are going to be n plus 1 multiplied by n minus 1, n multiplied by n minus 2, so on and so forth. Okay. So, this as a result what we are going to get is the total number of addition subtraction step is just sum of these, and the total number of multiplication division steps is just sum of this particular thing. So, in other words, the total number of addition subtraction steps are going to be summation I multiplied by I minus 1, where I goes from 2 to n, okay, because we have n minus the total number of steps are n minus 1, as a result this goes from 2 to n. 2 to n is going to be the total number is going to be n minus 1, okay, and this we can write this as summation say k equal to 1 to n minus 1. So, we have k where k is going to be just I minus 2, right, sorry, I minus 1. So, this we can write this as I minus 1 multiplied by I minus 2, where k sorry I multiply I plus 1 multiplied by I, or k plus 1 multiplied by k. Yeah. So, from k going from 1 to n plus 1, and this is going to be equal to summation of k plus k square, okay, summation k equal to 1 to n minus 1 of k is going to, it is nothing but 1 plus 2 plus 3 up to n minus 1. If we have up to n, the result is going to be n multiplied by n plus 1 divided by 2. If we have up to n minus 1, is going to be half of n minus 1 multiplied by n, okay, and summation of k square is from k equal to 1 to n minus 1 is going to be equal to 1 by 6 multiplied by k minus 1, sorry, n minus 1 multiplied by n multiplied by 2 times n minus 1 minus plus 1, 2 times n minus 1 plus 1, and that is going to be 2n minus 2 plus 1, 2n minus 1. Okay, which we can write this as n square minus n by 2 plus 2n cubed. So, n minus 1 2n minus 1 is going to be 2n squared minus 3n plus 1 multiplied by n is going to be 2n cubed minus 3n squared plus n divided by 6. Okay. So, these are going to be the number of addition subtraction steps. Okay. If these are the number of addition subtraction steps that we have, the leading term over here, so let us say if n is very large, say n is moderately large, say n is 10, even if n is 10, n cubed is one whole order of magnitude larger than n squared and 2 orders of magnitude larger than n. So, as the number of elements start increasing, or the number of variables start increasing, n cubed starts becoming larger much faster than n squared or n. As a result, the total amount of effort required is actually governed by this particular term. So, the number of addition subtraction steps, or effort in terms of the total number of addition subtraction steps, is of the order of n cube divided by 3 in case of Gauss elimination method, okay. And the total number of multiplication division step is n minus 1 n plus 1 multiplied by n minus 1 n multiplied by n minus 2 and so on and so forth, which we will be able to write it as summation I equal to 1 to n minus 1 and this is I multiplied by I minus 2, okay. So or sorry I multiplied by I plus 2. So at 1 it is going to be 1 multiplied by 2, so 1 multiplied by 2 plus 1 2 multiplied by 4 plus 3 multiplied by 5 so on and so forth up to n minus 1 multiplied by n plus 1. So this we can expand this as summation I equal to 1 to n minus 1 I squared plus 2 times summation I equal to 1 to n minus 1 2 I sorry 2 and this, okay. And this summation of I squared is the same as summation of this I squared. So again the order of effort is going to be determined by summation of I squared, where I goes from 1 to n minus 1. So for multiplication division steps also effort is of the order of n cube by 3. So in summary, what we have for Gauss elimination method is that the amount of effort required in solving a problem Ax equal to b scales as the cube, okay, not square, not linearly, but as the cube of the number of variables n. So when we start with an equation Ax equal to b, where x is an n dimensional vectors and we have n equations, if we were to use the Gauss elimination method, the amount of effort is going to be of the order of 2 n cubed divided by 3, because we have n cubed divided by 3 as the multiplication division steps and n cubed divided by 3 as the addition subtraction steps, sorry subtraction, okay. So that is the effort involved in Gauss elimination. In exactly the same manner we can also compute the effort involved in back substitution, and if we were to do that we will find out that the back substitution step scales as n squared and not as n cubed.